Hello, a very good evening to all my students and welcome to Swiflearn. Yes, so today we are also going to have a wonderful session, a wonderful discussion as we move ahead with our topic under discussion. So before we move ahead, let us talk about the platform that we are on, and that is Swiflearn. It is India's most sincere learning destination for classes right from 3 to 10. So all the grades from 3 to grade 10 will have wonderful sessions here. And they are 100% live and interactive classes where we have personalized attention, batches, right? Maximum batches will be of 6 students. You can also have one-on-one, just one student with a teacher or a mentor. We also have a wonderful dedicated team of mentors, the academic mentor team, which will track the work and the progress of each and every student. So isn't that great? Covers all the syllabus as per the school schedule, so you will not be left behind. That is the great thing about Swiflearn, this wonderful platform. The key features: having a detailed progress report given to the student and the parents, so we know how the student is performing. The parents are able to understand and assess the progress of their students, their children. Swiflearn Academic Test Series, the SATs. Yes, Swiflearn also has their SATs. So yes, you can take maximum benefit and advantage of these. You can take unlimited practice tests. You can also book a free trial class if you really want to try the platform. You can have subjective tests for the school exam so you know exactly where you stand and how you can actually predict how you're going to perform in your exam. So that is the best part about Swiflearn. Yes, for that, you need to subscribe to our channel, press the bell icon so that you keep getting notifications anytime there is a lecture, my lecture, or any other teacher's lecture. Don't forget to like and comment on the comment section. You can also give your doubts so we can actually solve your doubts here. And don't forget to share. So remember, subscribe to the Swiflearn channel and also press the bell icon. All right, so we have had two wonderful sessions previously on gravitation. Today we are moving on to the third session of gravitation. If you remember, we have talked about the universal gravitational constant. We talked about how you can derive the value of capital G. We have derived the value of small g, that is acceleration due to gravity. We talked about free fall, or free falling objects, exactly objects which fall from a height and the only force acting on it is the Earth's gravitational force. We went ahead and talked about and compared mass and weight. We also talked about how much a person will weigh on the moon, right? Because we talked about weight being dependent on that value of g, that is the gravitation, acceleration due to gravitation. So yes, since the small g, value of gravity, that is acceleration due to gravity, is going to change from planet to planet, our weight does change. So we had talked about how you can calculate this, right? We also then went ahead and talked about two entities, thrust and pressure. We actually derived the formula for pressure as well. And yes, this was a wonderful thing. We had a few numericals where the students also participated. So yes, it was a wonderful session. So today, let us start the session with moving forward with gravitation part 3. And let's see what all is in store for us today. Right. So today, what all are we going to learn? We're going to learn about pressure in fluid. So we did talk about pressure in last session, but today we are going to talk about pressure in fluids. We're going to talk about buoyancy. We'll also talk about why objects float or sink when they are placed on the surface of water. So this concept about why ships float, why an iron nail actually sinks, all this will be dealt in today's lecture. We'll also be talking about Archimedes Principle, a very, very important principle. And we are going to talk about relative density. We're going to relate the densities of objects with that of water. So we have lots of information in store today. So let us start the session. All right. So we have learnt about pressure and thrust in the previous class. If you are aware of this, we did talk about this. And we also talked about how will the thrust or pressure as well as thrust, how they are related. They are directly proportional. We have said whenever the thrust or the force increases, pressure will increase. And there is an inverse proportionality of pressure with the area in contact. So we had talked about a person standing on the seashore in the sand, how the feet sink into the sand. Whereas if a person is lying down, he will not sink as much as he would when he would be standing. So yes, that is exactly what we had talked about. So now in today's session, we are going to talk about how does this pressure apply with respect to fluids. Yes, with fluids. So let us see this. All right, so pressure in a fluid. Now, when we talk of pressure in liquids, as long as a pressure is, the liquid is confined within the container and it is not moving or flowing, pressure in liquids acts equally in all directions. Right? So this is one thing that, yes, so okay, so I think now everything is fine. So shall we start and continue with the session? Okay. Yes, so I'm continuing. All right. Yes, so we were talking about pressure in a fluid, right? And yes, so as we said, when a liquid is placed inside a container and as long as it is not flowing or not moving, then it exerts pressure equally in all directions. And this pressure is perpendicular to the surface of the object. So if I'm talking about, I place an object inside a liquid and the liquid is contained inside a container and it is not moving, then we can see that the liquid exerts pressure which is perpendicular to the surface and it is equal from all sides, right, left, above, and below. This is something which we need to understand. Okay. So when we're talking about fluidity and pressure in a fluid, we definitely know that along with the liquids, we also have gases. Fluids, when we talk about fluids, it is also both the things. When we talk of a liquid and a gas, both are fluids. So we'll talk about pressure in gases as well now. So pressure in gases is also, gases exert pressure around things. So like liquids, pressure in gases also acts equally in all directions. So that is something which is you have to understand and remember. So equally in all directions, both in liquids as well as in gases, as long as the gas is not moving or not in motion. Okay, so these are the two concepts that we've learned about pressure in a fluid, that is in a liquid, as well as in a gas. All right. Now let us learn a little more about it. Let us take an example. If we have two spheres, half spheres, which have been joined in such a way that all the air inside it has been sucked out, so a kind of a vacuum is created, then the air pressure which is acting on the outside will keep both the spheres stuck together. We are not having anything which is sticking the spheres together. Remember that. Only thing is we have removed all the air, sucked out the air from inside these two half spheres, and you will see that both these half spheres will remain stuck to each other basically because of the pressure being exerted from outside. So that is something which we have to understand about pressure. Right, so let us now talk about in a fluid, variation of pressure with depth. So as you go deeper and deeper into the water, how does the pressure change? So we know volume of water is going to be A into H, where A stands for the area and H is the height of this water column. So when we multiply by the both, we get the volume, right? All right, so let's move ahead. Now we are trying to compare the variation of pressure as we go deeper and deeper into fluids. Now we know mass of water is nothing but density into volume, basically because density is equals to mass upon volume. So we know this is going to be rho into V. So we already know volume when we talk of the liquid here is going to be area into H. So it is going to be rho into A into H, the density into area into height of the liquid column. Now we also know the force that is exerted is equal to the mass multiplied by g, that is acceleration due to gravity. We already know that. So the force is nothing but the entire weight of the water. So that is nothing but mass into g. So we already know mass is rho into A into H. So we get force equals to rho into A into H into g. Okay, we move ahead with this derivation. Now, we also know pressure is force upon area. We have already discussed about this in the last session. So yes, pressure is force upon area. So we already know P is equals to F upon A. So already we have derived the entire F. So it is going to be rho into A into H into G. This is the density into area into height of the water column into acceleration due to gravity upon area. So what happens is A and A gets cut. What remains is rho Hg, or we also take it as H rho G. So this is the pressure exerted by the liquid column. Okay, so equation which is used to collect or calculate pressure of a liquid at a particular depth. So if the depth is taken as H, then we can write it as rho Hg or H rho G, where H is the height, rho is the density of that liquid, and G is acceleration due to gravity value we already know. We have calculated that. Yes. Now let us talk about atmospheric pressure. Now, what is the pressure or atmospheric pressure? When we talk of atmospheric pressure, it is nothing but the pressure exerted by the atmosphere. Simple. So it is the force exerted per unit area by the air particles. What are we doing? We are actually connecting the idea of pressure, that is force acting per unit area, and trying to apply it to pressure exerted by the atmosphere. So what is atmospheric pressure? It is nothing but the force exerted per unit area by the air particles. We have to understand as we go higher, this atmospheric pressure decreases. That is, decreases with elevation or as the height from the ground increases. Why is that so? Because then ultimately this distance is going to reduce. So as we are going higher and higher, the value of H decreases. So atmospheric pressure will also decrease. All right. That's an interesting concept. So let us go through some questions and answer them. Write the equation to calculate pressure in water at a depth of H. So we are having the depth of H and we have to write the pressure. We already know to calculate the pressure at a depth of H, F, that is a force, is equals to rho into G into H, where rho will be the density of that particular liquid. G is acceleration due to gravity, and H will represent the height. All right. So now that we have talked about pressure exerted in fluids, and we are going to talk now about the buoyancy, a wonderful concept. And we're also going to talk about buoyant force. Now, what is that? All right. Let us talk about the buoyancy or buoyant force. Yes. Now, you know this concept about flotation and sinking, right? When objects float, some objects sink. So, how does this happen? So, when we talk of a buoyant force, something which keeps an object floating, this is called as buoyancy, and the force which causes this buoyancy is called the buoyant force. So, it is nothing but the upward force exerted by a fluid which will oppose the weight of the immersed object. So you must have noticed whenever you try to push a ball or a mug into an empty mug into a bucket of water, yes, you get that initial resistance, right? So there is something which is trying to push this mug or that particular ball up. Yes, that is the buoyant force, the upward force which is exerted by the fluid in that container and which is opposing the weight. The weight is acting downwards and this buoyant force is acting upwards. So you can see this is exactly what we are talking about. The buoyant force, this is the weight of the object which is acting downwards. So if you see here, when the weight of the object, that force is more than the buoyant force which is acting upwards, the object will sink. And when the buoyant force which is acting upwards is more than the force of the weight of the object, then that object will float. This is a simple concept when we try to apply our idea about the buoyant force with flotation and sinking. So let us learn something more about this. All right, so let us talk about the buoyant force now. All right, so when we talk about the buoyant force, it is the force and it is the result of the increasing pressure when depth inside the fluid is increased. So as you go more and more down, depth is increasing, the pressure keeps on increasing, and that is the buoyant force that we are talking about. So that is why it is very, very important for us to understand this. And if you can see here, there is net force exerted by the water from the bottom. You have a net force exerted by water on top, net force being exerted by water on all sides, because we had talked about fluid exerting pressure perpendicular to the surface of the object from all sides. So when the pressure on the top of the object is less than the pressure on the bottom of the object, we get an unbalanced force, right? So this is exactly what we are talking about as an unbalanced force. So what is happening is, from the top, the pressure is less, and from the bottom, the pressure is more. So from both the sides, ideally, it should have been a balanced force from all sides. But when this buoyant force is more than the force or pressure from the top of the object, this is an unbalanced force here. And that is what gives rise to a difference, either flotation or sinking. So buoyant force acting on any object will depend upon the following factors. Firstly, it will depend on the volume of the object that has been immersed into the liquid or the fluid, and also the density of the fluid. So let us see how buoyant force acting on any object is going to be affected by these two factors. That is, volume of the object or the body that has been immersed and the density of the liquid. Okay. So buoyancy is property. Can you see this ball floating on water? Yes, it is this upward force which is acting from below. So it is the property of fluids to apply a buoyant force. So every time when you talk of a fluid, always it will have an exert a force which is directed upwards. This we call as the buoyant force. And this property is buoyancy. Then let us try to apply this concept of buoyant force with aspect of sinking and floating. Now, if the buoyant force in the upward direction is less, simple. Let us now try to understand. If this buoyant force, which is acting in the upward direction, is less than the weight of the object. So what is happening is, weight of the object is going to act downwards. And this force, which is acting upwards, is less. So what will happen is the net force which is going to be there will be more in the downward direction. So the object will sink. Simple concept. So because of this unbalanced force, the force from down, the buoyant force which is acting upwards is lesser than the weight of the object which is acting downwards. As a result, the net force is going to be in the downward direction, and so the object sinks. Okay. Now let us talk about how an object floats. So simple. If the buoyant force in the upward direction, now we're going to connect the similar idea of buoyant force. If the buoyant force in the upward direction is more than the weight of the object, right? So this force in the upward direction is more than the weight which is acting downwards, the net force is going to be in the upward direction, so that object will float. So can you see here, the buoyant force acting in the upward direction is more as compared to the weight of this particular object which is acting downwards. So net force is going to be in the upward direction. So that makes the object float. Okay. So isn't it now so easy? Now we can actually compare and understand why objects sink, why objects float. Okay. So let us move this concept forward and try to understand how we are going to calculate this buoyant force. So buoyant force, when it is equal to, is always equal to the weight of the displaced fluid. So you must have seen whenever you try to force a mug into a bucket full of water, you must have seen water or the fluid getting displaced. So this buoyant force, which is acting in the upward direction, is equal to the weight of this displaced fluid. Or another way of calculating this is buoyant force is equal to weight of the object in air minus weight of the object in water, right? So buoyant force, BF, we can also write it as FB, force buoyant, is equals to weight of the object in air minus weight of the object in water. So understand this, remember this formula. Okay. So now let us talk about a condition of equilibrium of floating and submerged bodies. So submerged, completely inside the water, and floating objects. So let us see exactly what is this. So let's first talk about positive buoyancy. Simple, positive, it means the buoyant force is greater than the weight of the object, which is acting downwards. So the object will float. So when buoyant force is more than the weight of the object, we call it as a positive buoyancy, and the object will float when there is positive buoyancy. So what does neutral buoyancy mean? In this, buoyant force will be equal, so both will be balanced. So in that case, the object gets suspended in the fluid or in that liquid. Why? Because the buoyant force and the weight of the object both are balanced, they're equal. So the object will be suspended in the fluid. It's a simple understanding which we can very easily apply when we try to compare these two forces, weight of the object, buoyant force acting upwards. Isn't it simple? Okay, so then when we talk of a positive buoyancy, we talk of neutral buoyancy, definitely we're also going to have a concept of negative buoyancy. So simple, in this, the buoyant force is less than the weight of the object. So what is going to happen? Weight of the object is more, acting downwards, the object will sink. So you had one concept, positive buoyancy, object will float. Neutral buoyancy, when it will be suspended in the fluid because both are equal or balanced. And negative buoyancy, when the weight is more than the buoyant force and the object will sink in the fluid. Okay. Right. So now let us talk about a question that comes to everybody's mind. Ships, huge ships. Actually, they are made of iron, such heavy ships. But how do they float then? Shouldn't they be, because their weight is more, right? So they should be sinking. Why is this? Why do they float even though they are made of iron and they have more weight? Is because the ship is hollow from within. So what happens is the weight of the water that is being displaced by the ship is more than the weight of the ship. So it displaces the fluid much, much more than the actual weight of the ship. And also it is hollow from within. So as a result of which, what happens is the buoyant force acting from below on the ship will be more than the actual weight of the ship, even though it is made of iron. So as a result, ships will float in the water. So one thing, they are made hollow from within. Secondly, they displace water much more than the weight of the particular ship. So buoyant force will be more acting on the ship, and the ship will float, even though it is made of iron, and we would expect it to sink. So as a result of which, when will a ship sink? You know about the Titanic. Yes, what happened was basically because of it going and dashing against the iceberg, there was a kind of a dent or a gap made, water entered into it. So what has happened? The hollowness has disappeared. Now what has happened? Water fills inside. So that makes it heavy. And that is the reason why the ships can sink. Okay. So then a question, if I really compare an iron nail, okay, with a ship, you can see the great difference in the weight of an iron nail and a ship made of iron, right? So if I take an iron nail and put it in a glass of water, it is definitely going to sink. Why is that so? We talked about the ship which is made of iron not sinking. Why will an iron nail then sink? Because iron nail is compact, it is solid, it is not hollow from within, right? It is fully solid, compact, and the weight of the water that it displaces is much less than its own weight. So buoyant force is going to be lesser, weight of the nail is going to be more, and it will sink in that glass of water. Simple. Now you can actually apply your idea about buoyant force and the weight of the object. Try to understand the amount of water displaced by the object and try to compare these things. You will be able to very easily understand why objects sink and why some objects float. Okay. Now we also know the concept of being suspended in the fluid as well. Neutral buoyancy, where buoyant force and the weight of the object are going to be equal. Let's move ahead and let's answer this question. What do you mean by buoyant force? So we're talking about BF, or you can also write it as force buoyant. So let us answer this question. It is the upward force exerted by a fluid which opposes the weight of the immersed object. So whenever I try to immerse an object inside water, the weight of that object will be there, and there will be a force which is acting, exerted by the fluid in the upward direction, which opposes this weight of the object which is being immersed in that fluid. Simple. So now let us talk about density and the relation of buoyancy to density and relative density also. So now we are going to try to relate densities, okay, of different fluids and objects. And now first let us learn about the relation between density and buoyancy. Now let us see how this works. Okay. All right, density and buoyancy. So first we'll try to compare these two. Okay. Now when object which has a greater density than the fluid in which it is being immersed, it will definitely sink in that fluid. But if the density of that particular object is going to be less than the density of the fluid in which it is going to be immersed, it will float. So simple. Now we are actually trying to compare density and buoyancy. So from density, how will I come to know whether an object is going to float or sink? So when an object has a density greater than the density of the fluid in which it is being immersed, it is going to sink in that fluid. And if the density of an object is less than the density of the fluid in which it is being immersed, it will float. Okay. So we know density of any substance is the mass per unit volume of the substance. So you know density is equals to mass upon volume. So it is a ratio of mass and volume. Now unit of density we already know is kilogram per meter cube, because mass is kilogram, volume is meter cube, L into B into H. Okay. Now the density of a given substance remains the same under specified conditions, and it is different for different substances, of course. So density is going to change as its substance changes, but for a given substance it is going to remain the same. So the density of a given sample of a substance can easily help us to determine the purity of the substance. How? Let us see. We'll try to now talk of relative density. Okay, so when I'm talking of relative density, it is a very convenient way how we try to relate the density of a particular substance and compare it with the density of water. So relative density is a convenient way to express density of any substance in comparison to the density of water. So relative density of any substance is ratio of the density of that substance to the density of water. So we know relative density is ratio of similar quantities. So it has no units, because density of the substance and density of water both have the same units. So same quantity. So you will have no unit. Remember, relative density has no units. Okay. So now we talked about relative density. We talked about how density can be connected with buoyancy. Density of a substance, an object being more than the density of the fluid in which it is immersed, it is going to sink. Density of an object less than the density of the fluid in which it is being immersed, it will float. So now we are going to talk of sinking and floating of objects in water. Now we are actually taking the fluid as water. So when the density of an object is more than density of water, the object will sink. So this also applies with respect to water as a fluid, as a liquid. For example, the density of an iron nail is more than density of water. So that means what? The upthrust of water on the nail, iron nail, is going to be less than the actual weight of the nail. So the nail sinks. Simple concept. So here we are trying to actually talk of density with relation to water, density of water, and we are trying to understand whether an object will float or sink. Right. So we have already talked about this as well. So sinking and floating, when the object, the density of an object is less than the density of water, the object will float. So in one concept, we said when the density of an object is more than density of water, it will sink. So similarly, when the density of an object is less than the density of water, the object will float. Let us take an example. For more density of the object being more than water, density of water, we talked about iron nail. Here we are going to talk of cork. You take a cork and put it in a glass of water, you will see it will float on the surface of water, because the density of cork is less than the density of water. So upthrust of water on the cork is greater than the actual weight of the cork. So the cork will float, because you can see water is exerting upward pressure. The buoyant force is going to be more because the density of that particular object is less, that is cork is less than that of water. So let us answer another question. The question is, why does a block of plastic released underwater come up to the surface of water? So let us just compare it with, say, a mug made of plastic. So block of plastic, mug of plastic, you keep it below water, and when you leave it, it will come up to the surface of water. Why does this happen? Okay, because the density of plastic is much smaller than that of water. So force of buoyancy acting on the plastic block is larger than the actual load of the weight of this plastic block or the water that it is displacing. So due to this larger force of buoyancy, which is acting upwards, The plastic block which has been released underwater comes up to the surface because the buoyant force is pushing it up. Because the weight, the density of that particular plastic block is much, much less. And the amount of water also displaced is very less. So buoyant force is going to be more. Simple concepts when we actually understand what is buoyant force, how we compare it, or compare it with respect to weight of the object, compare it with respect to density of the fluid in which an object is being immersed, and the density of that particular object. All these things make it very easy for us to understand the idea of flotation and sinking. So we are moving ahead with a very, very interesting concept, Archimedes Principle. Let us study this. So what is Archimedes Principle? It states that when a body is either immersed fully or partially in a fluid. Now, fluid can be liquid or it can be gas. It experiences an upward force which is equal to the weight of the fluid that is displaced by it. So the upward force here, we mean the buoyant force. So what does Archimedes principle say? That whenever an object is either fully immersed in water or partially immersed in water, it experiences an upward force that is nothing but your buoyant force, which is equal to the weight of the fluid displaced by it. You will see always fluid being dispersed when you try to immerse an object inside a liquid. Okay, so let's see how we can. We'll take a Eureka can. Can you see this can, which is having a spout, a kind of a spout from the side? We call this as a Eureka can. And it is filled up to its spout. Then take a stone, weigh it first in air because we want to know the weight of this stone in air. Right. So we take that as W1, weight of the stone. That is going to be the object which we are going to immerse. All right. Now, when we immerse, we are trying to verify Archimedes principle. The moment we immerse the stone inside the water in the Eureka can, we know water is going to overflow through the can. Yes, through the spout, it is going to overflow, and we are actually collecting it. Collect this overflowing water in a beaker like this. Now, as you are immersing, you will see that the weight of the stone is reducing. So take the weight of the stone when it is in water. We'll take it as W2. So W1 was weight of the stone in air. W2 is going to be the weight of the stone in water. Now we will see that W2 is definitely less. Can you see? It is only 3 kilograms. Initially it was 5 kilograms. Inside the water, it is going to be 3 kilograms. So it is less. So W2 inside the water is less than W1 when the weight was in the air. But this is due to the upthrust. So that force which is acting upwards is which is provided by the water, as a result of which there is an apparent loss in the weight, which will be equal to W1 minus W2. That is weight of the stone in air minus weight of the stone in water. Okay. So we are trying to still verify. Now, if you see, we have collected the water which has been displaced through the Eureka can when we immersed that solid into the liquid. That if you measure, which is collected, we will find that that loss, that is W1 minus W2, will be equal to the weight of this water displaced by the stone when it was being immersed in water. So this is exactly what Archimedes principle talks about, that it is equal to the water displaced by that particular solid. Yes, so this is how we have actually verified. We weighed the stone in air. Then when we were immersing in water, especially in a Eureka can, because we can collect the displaced water very easily, and we are also measuring that, the weight of that. So the difference in the weights will be equal to the weight of the water which has been displaced. W1 minus W2 will be equal to the weight of the displaced water. Okay, so we have actually verified Archimedes principle. Now let us see where we can actually apply this Archimedes principle. It is actually used in designing bodies like submarines and ships. When we talked about a ship made of iron, not sinking when it is in water. We had talked about it displaces water much more than its weight. So as a result of which, the buoyant force is going to be more, right? So this is exactly how the people, the engineers who are actually designing the bodies of ships and submarines. Ships need to float, submarines need to sink into the water. That is where they apply Archimedes principle, take the weight of that particular ship or the submarine, and that is how they work on designing the bodies. Right. It's also used in making hydrometers. Now, what are hydrometers? Hydrometers are used for determining density of liquids. Another important thing, they're used in making lactometers. Lactometer is used to determine purity of a sample of milk. So we have various applications of Archimedes principle here. So let us answer a few questions. If the volume of a 500-gram sealed packet is 350 centimeter cube, so we are having the volume and you're having the mass as well. Will this packet float or sink in water if the density of water is 1 gram per centimeter cube? And what will be the mass of water displaced by this packet? So we have two questions here. One thing is we have to determine whether the packet will float or sink in water when we know the density of water. So for that, first, we have to calculate the density of that particular sealed packet, right? So that then we can compare. Secondly, they have talked about what will be the mass of water displaced by this packet when it is being immersed in water. So let us start the working. Okay, so first we will calculate the density because we have to compare it with density of water, and that will tell us whether that packet will float or sink. So we know density is equals to mass upon volume. So 500 upon 350 works out to 1.428 gram per centimeter cube. And we know the density of water was 1 gram per centimeter cube. So if you see this value, the density of the packet is more than density of water. 1.428 gram per centimeter cube is definitely more than 1 gram per centimeter cube. As a result of which, we can be very, very sure this packet will sink in water. So our first question is answered. Now let us move ahead with the second. We have to calculate mass of water that is being displaced by the packet. What mass of water which is being displaced by the packet is nothing but equal to the volume of the packet. That is going to be 350 grams. So simple, mass of water which will be displaced will be equal to 350 grams. Simple, isn't it? So when we actually apply principles, concepts, and we actually see, once we are clear with the concepts, we are clear with the principle, it becomes so easy to calculate or work out your numericals. Okay. So what are the things that we have learned today? We learned quite a lot of things today, much more things like pressure, more detail. We talked about pressure in fluids. We talked about an important concept called as buoyancy. We also discussed why objects float or sink when they are placed on the surface of water, where here we compared them with the weight and buoyant force, the upward thrust, up thrust from the water, the upward force, when it is balanced, when it is weight is more than a buoyant force, when buoyant force is more than weight. So we saw all the various conditions. We also talked about Archimedes principle, and also remember, we also did compare densities with the concept of density, with the concept of density of the fluid in which a particular object is being immersed, and whether on the basis of that, we can guess and make out whether the object is going to float or sink. We talked about a very important principle, Archimedes principle, which has got a wide range of applications. And we also talked about relative density, where we are comparing the densities, or relating the density of any substance, any liquid with that of water, because we know the density of water. It is 1 gram per centimeter cube. So this is what we have actually learned today, thrown light on a lot of topics. So yes, hope it was a very interesting session for all of you, and many of your questions are answered. You need to know that what are the different questions that can be asked. We have actually gone through those questions, the numericals, how they're going to come, how we are going to connect these things. So let's hope it was a very good session. If you have any doubts, please ask them in the comment section. We'll definitely answer them. So yes, hope you enjoyed the session today. Have a very good evening. Bye-bye. We'll meet again, same time, 7 o'clock, with much, much more interesting facts in science. Thank you and goodbye.